Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we are going to look at a kind of simple example of a bolted connection. We have a connection that we're given, we're going to check it, and we're going to see what the total strength of this connection is. So how much load can we put on this connection? Our connection is in tension. We have a wood member in the center, sandwiched by two steel members, one on one side, one on the other side. You can see the cross section. And so the steel members we're not going to talk about. We're going to assume that the steel member is designed to be adequate, and we're going to check the resistance of the wood side of this connection, basically. Yeah, this connection has pretty big bolts for a wood connection. So these are 1-inch diameter A307 bolts, so they're pretty chunky for wood, but it's a pretty sizable piece of glulam. We are going to have to check in this only the parallel to grain resistances, because we don't have any component of load that is perpendicular to grain. So we're going to have to check our row shear strength, right, which is pulling out these plugs out the bottom of the piece of wood like this. We are going to have to check our group tear out. Whoops. We're going to have to check our group tear out, which looks like this, as you recall. Then we're going to pull this plug out of the bottom of the piece of wood, right? There's our piece of wood. And we are going to have to check net tension, which is where we fail the piece of wood all the way across. So remember, for all of these failure cases, these bolts are going with the steel plate. So this is the way that the steel plate is going. The bolts are going with the steel plate, if we're looking from the point of view of the wood, and all of the bolts have to go out of the piece of wood in order for the connection to fail. So those are all of our failure modes that we are going to check. Okay, so we are given that we have dry conditions and standard term loads, so we can already pick out all of our modification factors. So standard term loads means we're checking for a KD of 1.0. KSF equals KSV equals KST equals 1.0, because we're talking about dry conditions. So service condition factors are all 1. We're untreated, so KT equals 1. And KH, which we're not actually going to have to use anywhere, which is system effect factor, is also 1.0. Okay, so let's start with some data about the about all of the pieces of this. Okay, so we have our bolts and we have our wood. So our bolts are 1 inch. So the DF, which is the diameter of our fastener, is 25.4. So let's just say 25 millimeters. And the hole size, which we cannot forget to consider, is going to be 25 plus 2 equals 27 millimeters. Okay, so we have a 27 millimeter hole with a 25 millimeter bolt. And the hole, as always, we're assuming that it's 2 millimeters larger than the bolt. Okay, and then we have steel plates. And the FY, so this is, this steel plate is A36. And the FY for A36 is 250 MPa. And the FU is 400 MPa. So we're going to need these numbers later. This is FY, by the way, for the plate, because we also have an FY for the bolt, which we're going to use later. So let's not get those confused. Okay, so the first thing that I like to do in this problem is check our spacing requirements so we can get some practice looking at the spacing. Okay, so we can see the bolt spacing in the member. We're going to check our row spacing, our unloaded edge distance, our loaded end distance, because we do have a loaded end in this problem, right? This end here is a loaded end because the bolts are pulling towards it. Okay, the top and bottom here, these are unloaded edges because there's no load from the bolts going towards them whatsoever. We're going to have to check the spacing of the fasteners. Okay, so let's do spacing, check spacing. Okay, so this is the spacing between the rows. Okay, and that's the spacing in the perpendicular to grain direction. So I'm considering both ways of talking about it because the approach is a little different in 08614 versus 08619, although the requirement is exactly the same. So here we have our S. This is SC. And we find what that spacing is up here. So it's right here. This is the spacing between the rows of bolts. If these are the rows, that's one row, that's two rows. So the rows are in the direction of the loading. So spacing between the rows, so it's like the column spacing is 75. That's SC in 08614. In 08619, that's called basically the perpendicular to grain direction spacing, and that is the SQ. So these are the same thing, both of these. So SC equals SQ equals 75 millimeters is what that spacing is. And what is our requirement? I don't want to say over. SC or SQ needs to be greater than or equal to 3df is the requirement. And you can look that up. 3df is 3 times 25, which equals 75 millimeters. So it does satisfy the requirement, just barely, like exactly. Okay, let's check the other vertical direction one, which is our unloaded edge distance. Okay, and what is our unloaded edge distance? Let's take a look. Okay, so that is this distance here. Oops. Okay, so this thing is centered. So this is our EP here. Okay, our unloaded edge distance. And so it's going to be the total height, which is 304. So the size of this is given, right? So this is 304. And so this is 304 high. The thickness is 130. Okay, so it's 304 minus 75. Okay, and then divided by 2. So this is EP. What the actual EP is 304 minus 75 divided by 2, which is 114.5 millimeters. And the requirement for EP is that EP must be greater than or equal to 1.5 df. Okay, and that equals 1.5 times 25 equals 37.5. Or EP also has to be greater than 0.5 times SC, 0.5 times 75, which also happens to equal 37.5 millimeters. Okay, so you might recall EP has to be greater than the maximum of 1.5 df or 0.5 SC. So I'm checking both of those and they are okay. So unloaded edge distance is fine. Okay, let's check the next one, which is loaded end distance. Okay, so what are we looking at here? We're looking at this distance here, right? That's our AL, which is our loaded end distance. You can see that the value is 175. And AL, the requirement is that it has to be greater than 5 times DF, which is equal to 125 millimeters, and also has to be greater than 50 millimeters. Okay, so those are the two, right? So for loaded end distance, the requirement is it has to be greater than the max of 5 df or 50 millimeters. And you can go back to the other notes or the standard, the drawing in the standard, to see what those required distances are. Or you can have that with you. So therefore, this one is okay as well, because 175 is greater than both 125 and 50. And the last requirement that we have to check is spacing of fasteners within a row. So this is the parallel to grain spacing. That's the same thing. And the actual spacing there is this value here, which is 100. That's the spacing within a row. And that's in the parallel to grain direction. So those are the same. That's either the SP or the SR. So SR in OD 614. So SR equals SP equals 100 millimeters. And the requirement is that SP or SR has to be greater than or equal to 4 times DF, which equals 100 millimeters. And so that is fine too. Okay. Just barely. So it looks like what the designer has done here, and I know this because the designer is me, is took those minimum spacings and just used the minimum spacings for most of these. So the bolt group is as close together as it could possibly be. Takes up the least amount of space by using those minimum spacings. Okay, so now we check the spacings. Spacings are fine, so the connection's okay. Now we're going to go through each of the failure mechanisms, the failure modes, and check each of them in turn. And we're going to do them in order, starting with the yielding resistance. Okay, so first thing we're going to have to find NU, which is our unit yielding resistance, unit bolt resistance, basically from the Johansen yield equations. And to do that, we're going to have to know our embedment strengths. Okay, so we have to find the embedment strengths for F1 and F2. In this case, when we have a 3-member connection, member 1 are the side members, so that's the steel members in this case, and member 2 is the center member. So the side members are 1, so it's going to be F1 and T1, so T1 is going to be the thickness of the steel plate, which you can see is 6 millimeters here. And member 2 is the center member, the middle member, and so T2 is going to be the thickness of that member, which is 130, and F2 is going to be the embedment strength of that member, which is the wood one. So member 1 is steel. I'll just say this one is member 1, and these ones are member 2. Okay, so now when we want to calculate F1, which is our embedment strength for steel, we're going to say this one, member 1 is steel. It's A36. A36 is like a structural steel. So this is a mild steel. So therefore, I'm going to get these values for KSP and phi steel, right, which we talked about when we talked about yielding resistance. And then my F1 is this equation. And we already calculated what FU is. And this is 0.8 divided by 0.8, which is 1. And FU for the plate, we figured out already, is 400. So we get 3 times 400, so F1 is equal to 1200 MPa. Okay, so F2, member 2 is the middle member. Okay, so remember there's our Fi theta, which is our embedment strength at any angle. And that's an interaction between FIP, which is the parallel to grain embedment strength, and FIQ, which is the perpendicular to grain embedment strength. Since my only load component is parallel here, I don't have to bother doing that interaction. It's just that Fi theta equals FIP. And I'm only going to have to calculate the parallel to grain embedment strength, which is this one. Okay, so I need G and I need JX. So to find G, I go to this table, A12.1 in the appendix, and we are dealing with a Douglas fir larch glulam. So we're looking at glued laminated timber here, Douglas fir larch. So that means our G is going to be 0.49. Our JX is 1.0 because we're not CLT. So now if I sub this all in, I get 18.4 MPa. And so therefore my F2, which equals my Fi theta, which equals my FIP, is 18.4 MPa. Easy peasy. Okay, this is because theta equals 0. You know, if you plug in theta equals 0 into that interaction equation Fi theta, you'll see it comes out as Fi theta equals FIP. And we talked about that when we introduced that equation. Okay, so then I need my Fy, which is my bolt. And that's given in the standard to be 310 MPa. And then I need my thicknesses. So my T1, remember, member 1 was my steel, which we already determined was 6 millimeters thick. And T2 is my wood, which is 130 millimeters thick. So if I go back just to show, so the steel plate is given as 6 times 150, so that's 6 millimeters thick. And you can see my glulam as 130 thick. That's those numbers there. Okay, so now we know everything that we need in order to do the Johansen yield equations. And which ones are going to govern? This is a 3-member connection, so only the 3-member Johansen yield equations are going to apply, and there's only 4 of them, so that cuts down some of the work. Okay, so it's only A, C, D, and G that are going to apply. So I am going to calculate those. I'm just going to give the answers, basically. Well, I'll calculate out the first one, but the other ones are gonna... Okay, so F1 is 1200, DF is 25, T1 is 6, and I get a value of 180 kilonewtons. That's after I convert from newtons into kilonewtons. Okay, so when I calculate all of the appropriate Johansen yield equation strengths, unit strengths for an individual bolt, I get these 4, 180, 29.9, 55.1, 38.2. And so we find that the 29.9 is the one that governs because it's the lowest one. So therefore, the NU that I'm going to use in my overall yielding resistance is now 29.9. So now I'm going to calculate my overall yielding resistance. Okay, so we have 2 shear planes. We have 6 fasteners in the connection. So now if I calculate my NR, I get 0.8 times NU, which was 29.9 kilonewtons, times 2 shear planes, times 6 fasteners. And I get that my total NR, if I can write a nice N, equals 287 kilonewtons. Now there's one thing that I actually forgot to do out explicitly in my haste to go through this part. I forgot that in between Fi theta and Fp, there is Fi theta equals Fp times Kd Ksf Kt. So that's where those come in. But so basically, this simplification is still because only load component is parallel. So theta equals 0. So then down here, this equals Fi theta equals Fip because Kd Ksf Kt equals 1.0 in this case. But if those were not, then I would have to add those in between calculating my Fip and assigning it to my Fi theta. Okay, so it doesn't make any difference to the numbers here, but just so that we don't miss that step. That's where those would go. Okay, so now we've managed to calculate our full yielding resistance. So that is one of the failure modes that we need to check for this connection. Okay, so the next one is we need to look at our row shear resistance. Okay, so the first step in the row shear resistance is that I need to calculate the row shear resistance for each individual row of bolts. And so you'll recall that for this question, I have 2 different rows of bolts. I have 1 row here, and I have 1 row here. Each of those has 2 shear planes, and I'm going to calculate each one separately. Now, in this specific example, both of these rows are identical. So when I calculate one, the shear resistance of one of them, the other one is going to be the same. So recall that this is the equation, and I'm going to start with, so this is member 1, row number 1. So that's the ij. And this is the equation. Okay, so I have to find all of those different parameters. Okay, so first of all, what is my FV? I'm going to get my FV from table 7.3. So let's recall, since we haven't done this a bit recently. So remember, this is where I get all my strengths. So I'm talking here about a Douglas fir larch glulam beam 24 FEX. So that's this one here, and I read down to my longitudinal shear, it's 2.0 MPa. So that's the value that I'm using here. Okay, now what about my, KD, KSV, KT? We already talked about those being 1. So what about the next parameters, KLS? Remember that for the center member in a 3-member connection, the stress distribution is pretty close to linear, so therefore my KLS equals 1. If I was talking about side members where I have a uneven distribution of stress across the width of the member, then my KLS would be 0.65. So this is a center member, so therefore KLS equals 1.0. Okay, my T equals 130. That's just the thickness of my piece of wood. So now what's my NC? That's the number of fasteners in a single row. It's the same as the number of space shear planes that we have. So we have here 1, 2, 3 fasteners in a row. That's going to result in one plane here, 2 here, and 3 here. Okay, so the number of bolts is the same as the number of bits of the shear plane that we have to add up. So that means for this question, our NC equals 3. Okay, so you remember that our ACRI, that's our critical length, is the minimum of the loaded end distance or the in-row spacing, which is SR in OED 614 and called SP, which is the parallel to grain spacing in OED 619, which are the same dimension. So let's look at those. So we have 2 dimensions. This one is our AL, right? This is our AL. And these ones are our SP, or our SR. Okay, so we need to take the minimum of those. So the minimum is going to be 100. So my A critical here is 100 millimeters. So I'm going to take 100 millimeters and multiply it by 3, and that's going to give me a conservative length for my shear planes that I'm shearing for my row shear. Okay, so therefore, if I calculate now my PR11, okay, I get 93.6 kilonewtons, and my PR12, which is my other row, is also 93.6 kilonewtons. So it's the same geometry. So both rows are basically the same. Okay, so then I calculate my PRIJ min, which is my minimum of all of the different rows. So here I have 2 rows. They both are the same. So the PRIJ min is going to be whichever one, it doesn't matter. So this is going to be 93.6 kilonewtons. Okay, so now I'm going to find the total factored row shear resistance for that member. If I had 2 members on that side of the connection, I would have to do this twice. In this case, I only have 1 member on that side of the connection because I have 2 steel plates on one side of the connection, 1 wood member on the other side of the connection. So basically here I calculate my PRR1, so that's for member 1 on that side of the connection, and that equals this. Okay, and my phi W is 0.7, my PRIJ min is 93.6 kilonewtons, and the number of rows is 2, so I have 2 rows. Okay, which is pretty clear if I look here. So I have 1 row, 2 rows, so those are my 2 rows. So I find the minimum row shear resistance for either of the rows, and then I multiply that by 2 since I have 2 rows. I include the material reduction factor, and I get 131 kilonewtons. So then, if I had more than, so that's for 1 member on that side of the connection. If I had more than 1 member on that side of the connection, like I had 2 wood members on that side of the connection and 1 steel plate on the other, then I would add those together. I would get a PRR2, and then I would add those together. But in this case, I only have 1. Okay, so find the total factor to row shear resistance for all members on that side of the connection. In this case, there's only one. So I have my PRRT equals PRR1 equals 131 kilonewtons, because there's only one member on that side of the connection. Okay, so that's the end of row shear. Okay, so now that I've calculated my row shear, I can move on to the next check, which is my group tear-out resistance. Okay, so we're going to find for our member one, which we only have one wood member again on that side of the connection, so we're only going to have to do that once in this case. Recall that this is the equation for group tear-out. Okay, so recall that we have one part which is the same strength as our row shear, but we take basically the average of the first and last row shear values. We have to make sure that value is in newtons when we do it. And then we have the component that is the tension component, right? So if we're looking at group tear out, we have basically one row shear here. That's a half a row shear for the first one here, which is half a row shear for the second one, because we only have one shear plane. And then we have this bit here, which is the tension bit, which I have to use the net area between the bolt holes. And that's the chunk that I'm going to take out of this piece of wood when I do my group tear out. Okay, so my phi W is still 0.7. Okay, recall. So this is why we usually do group tear out after we do row shear, because we can reuse the row shear values that we already calculated. So PR11 equals PR12, which is my PR1NR, right? So there's only two rows. So it's the first one and the second one are the first one and the last one. And that was equal to 131 kilonewtons, which equals 131,000 newtons. So I have to be careful and make sure that's in newtons when I want to add those together. Okay, and FT, I'm going to get from my table over here, right? So FT, I'm talking about 24 FEX Douglas fir larch. My FT is, I got 20.4. I'm supposed to use FTN here. Okay, because we are doing a net section check. Okay, so I'm not going to use the gross. I'm going to use the net, 20.4. Okay, so that's my TN, FTN, and then I have to calculate my APGI, right? APGI. So I need to find the distance between the bolt holes and then times the thickness of the member. So here I'm looking at the net area on this part here. So I'm going to take my 75, I'm going to subtract half a bolt hole on the top, half a bolt hole on the bottom, because 75 is center to center of those holes. And then I'm going to multiply that by the thickness, which is 130. Okay, so this is going to equal 75 minus 2 times half of a hole. I'm going to say D of a hole, the diameter of the hole, which remember is 27 millimeters, 2 millimeters bigger than the bolt. And then I'm going to multiply that by the thickness, which is 130. This is the thickness, right? And so I get 75 minus basically one bolt hole, which is 27, times 130. And I get 6240 millimeters squared. Okay, so now I can plug everything in. PGR1. Okay, so I get 131,000 plus 131,000 divided by 2. Okay, plus my FT is 20.4 times 1 times 1 times 1, because we're in dry conditions, times 6240. And I do all of that math, and I come up with 154,600 newtons equals 154.6 kilonewtons. Okay, so that is the group tear out for one member on that side of the connection. So I'm talking about the right side of the connection, the side that has the wood on it. And since I only have one member there, then my PGRT, which is my total group tear out resistance for that side of the connection, is 155. Now, I'm only looking at the one side of the connection in this case because my other side of the connection is steel. So when I check the other side of the connection, I'm going to have to use my steel course knowledge from S16. Let me just circle this one as well to be consistent. Okay, so I've got this was my row shear strength. This is my group tear out strength. So you can see that row shear is less. Is going to govern, it has a lower strength because in my group tear out, even though I have fewer shear planes to fail, I have to fail a part in tension, and that is very strong. Okay, so that's 3 out of 4. Basically, I've done yielding, row shear, and group tear out, and my last one here is net tension. Okay, so since we're doing glulam, so remember that in the net tension resistance, it refers back to basically our net tension checks from the lumber and glulam chapters, chapter 6 and chapter 7. So here I'm basically just going to check my my axial strength of my member in tension. Oops, this is MPa. And while I'm at it, I'm also going to go ahead and check my gross section strength. So FTN 24 FEX is what we're dealing with here. My FTN is 20.4. My FTG is 15.3. So I might as well check that one while I'm at it. Okay, so now I have to find my gross area and my net area. So my gross area is 130 by 304. That's the size of my glulam beam. So I get 39,520 for gross. And for my net, all I have to do is remove my bolt holes, right? So I have, I can remove the hole, or I can remove the whole length on my 304. There's, 2 ways that I can do it. I think it makes maybe more sense if I do it like this. So I do 304 minus 2 times the bolt hole diameter. Okay, so that's like my vertical dimension is 304. I take away the bolt holes, and so I get, remember my bolt hole is 27, and so I get 32,500 millimeters squared. Okay, let's check and make sure that we are within our 75%. Remember that AN has to be at least 75% of AG, or what I cut away. So if I do AN divided by AG, I'm going to get 0.832. And this is greater than 75%. So that's okay. Okay, so now I can do my tension checks. So remember that I need my capital FTN and my capital FTG, which are going to be multiplied by our KD, KST, KT, KH, right, if you remember. And those are all 1 in this case. So my FTN is just going to be my 20.4. And likewise, my FTG is going to be 15.3. Same deal. So now I have my TN R1. This is what I call my net tension strength for when I'm dealing with the connections, because this is my net tension net for resistance R for member 1, right? If I had 2 members on that side of the connection, I would repeat this calculation for both of those members. Like if I had 2 wood members, if I had one here and one here, and they were both pulling, like let's say I had a steel member in between 2 wood members, then I would have to calculate this net tension for both of those. So, and I'm going to include the gross in there. It's not clear for glulam whether you should also calculate the gross, I think, but I'm going to do it anyways. Times AN. Okay, so I get 0.9, 20.4, and my AN is 32,500, and I get 596 7 kilonewtons. Okay, then I'm going to check my gross. Okay, my gross governs as it almost always does. Okay, so then if I find my total net tension, then I get that my total net tension resistance on that side of the connection is 544. And I don't have to take a sum here because there's only one member on that side of the connection, which is that one wood member. Okay, so now I have gone through, I've calculated the yielding, I've calculated the row shear, I've calculated the group tear out, and I've calculated the net tension. Now I'm ready to check my overall requirements and make sure that everything matches. Now here I don't have an applied NF, so I'm going to try to calculate what is the NF that this connection would satisfy, like what's my minimum NF. Okay, which sounds complicated, but it's not so bad. Okay, so we're going to check the requirements. We're going to find what is the maximum NF that I can put on this connection. So remember, NF is my total connection load at any angle to grain. In this particular problem, I'm only looking at load in the parallel to grain direction. So basically NF equals PF, right? So PF equals NF and QF equals 0. Like, we're not going to bother to check, obviously, the perpendicular to grain strengths because I don't have any perpendicular to grain load. Okay, so therefore the requirements that I'm going to have to match, remember I have requirements A, B, C, and D. A is yielding, B is parallel to grain, C is perpendicular to grain, which we're not going to care about, and D is the interaction of parallel and perpendicular to grain, which we're also not going to care about in this case. So for the yielding case, NF is less than or equal to NR. And in the parallel to grain case, NF has to be less than or equal to PR. Okay, because NF and PF are the same. Usually it's PF less than PR. Here NF equals PF. So I'm going to use this to find what is basically the maximum NF that I can put on this. Okay, so let's check requirement A. So NR that we calculated for yielding before was 287 kilonewtons. Okay, so we have to meet that requirement. And requirement B, okay, is less than or equal to PR, which equals the minimum of all of these, right? We have our PR RT, which is our row shear, that we calculated as 131. We have our P GRT, which is our group tear out, which we found to be 155 kilonewtons. And we have our TNRT, which is our net tension, and we just calculated that to be 544 kilonewtons. Okay, so obviously this one is going to govern. Therefore, NF has to be less than or equal to PR, which equals 131 kilonewtons. Okay, and then requirements. C and D do not apply because we don't have any perpendicular to grain loads. Okay, so therefore overall, you know, if we're going to compare this one. So NF has to be less than or equal to 287, and NF has to be less than or equal to 131. So therefore, the lowest of these two is the NF less than PR, which was based on the row shear, strength of 131. So therefore, our total maximum connection resistance is going to be 131 kilonewtons, and the connection is expected to fail in row shear. You know, it's hard to predict exactly. You know, row shear and group tear out here are pretty close together, 131 and 155. It's totally possible that we could fail in group tear out. Remember that wood is a very variable material. Like, you know, if there happens to be a knot near that group tear out net tension area, or there's some other kind of imperfections there, then it's totally possible and probable that I could get group tear out instead of row shear. But for the purpose of the calculation, it's the row shear one here that governs, so that's what we would expect. Is this a good thing or a bad thing? I mean, neither really, but if we wanted this connection to be ductile, what would we do to change it? I mean, this is fine. We've calculated what the strength is. The strength is 131. If we wanted to revise this connection so it was more ductile, then we need to basically increase the row shear resistance relative to, and the group tear out resistance relative to the yielding resistance. How would we do that? We could use more smaller bolts, perhaps, so that we have more rows for our row shear. We could make that connection longer. Okay, that would help the group tear out. Probably if I spread my bolts over a larger area, then that will probably make the biggest difference. And so in order to do that, probably I would use smaller bolts. I mean, I made the comment at the beginning of this that we're using a 1-inch bolt, which is pretty chunky for timber connection, maybe even of this size. So if I use more smaller bolts, the other option would be to use something like timber rivets or nails instead, because then I can't get those non-ductile failure modes. Yep, so anyway, so that's the end of this example, how to calculate bolted connection resistance for a simple one, and we're going to follow this up with some more complex examples.